Hello to everyone. Welcome to the course on numerical linear algebra and application. Today we are going to have 49th lecture and 10th module of this course. We would be learning in this lecture some concepts related to eigenvalues of a symmetric matrix using the symmetric Langkos algorithm. In this lecture, we turn our attention to computing approximating eigenvalues of a symmetric matrix A using the symmetric Langkos method. We have remarked that when a beta j is exactly equal to 0, we have an invariant subspace. This is indeed a new concept. Unfortunately, this happens very rarely in practice. In practice, for large enough values of j, the eigenvalues of Tj provide very good approximation to the extremely eigenvalues of the coefficient matrix A. To answer the question of how well a ridge pair or Tj approximates an eigenpair of A, we state the following result. Let theta I yi be a ridge pair and let Ri is equal to Ayi minus yi theta, where I is equal to 1 to j. Then in each interval, theta I minus norm of Ri2 plus theta I plus norm of Ri2, there is an eigenvalue of A. Thus, it follows from the above theorem that Ri of 2 is a good measure of how accurate the ridge pair theta I yi is. It also turns out that norm of Ri2 can be computed cheaply from the square decomposition of Tj as shown in the following theorem. Now look at this theorem for symmetric Langkos ridge pair. Let Tj be the j over j symmetric triadiagonal matrix obtained after j steps of the symmetric Langkos algorithm. Let Stj, Tj, denote the real square form of Tj. Stj, Tj, Sj equivalent to diagonal of theta 1, theta 2, theta j, that is theta 1, theta 2, theta j are the eigenvalues of Tj. Let Vj, Sj is equal to Yj, that is y1, y2, y3, yj. Then for each I from 1 to j, we have norm of Ri is equal to norm of Ayi minus theta I yi, that will be equivalent to modulus of beta j Sji, where Sji is E transpose j Si. Si is the ith column of j. So the proof is the following. Norm of Ri is equal to norm of Ayi minus yi theta I, that will be equivalent to Avj Si minus Vj Si theta I. So that will be equivalent to norm of AVJ minus VJ TJ SI, because TJ SI is equal to SI theta I. Norm of beta J Vj plus E transpose J SI. Note that AVI minus Vj Tj is equal to beta J times of Vj plus Ej transpose, and that will be equivalent to norm of E transpose J SI modulus of Bj, that will be equivalent to mod of Bj Sji. Note that norm of Vj plus 1 2 norm is 1. A computable error bound combining theorem 1 and theorem 2, we obtain the following eigenvalue bounds for the eigenvalues lambda of A. Minimum of lambda theta I minus lambda is less than or equal to mod of beta k mod of sk for I is equal to 1 to etc. The bisection method for the tridiagonal symmetric positive definite generalized eigenvalue problem. As we have seen in several previous case studies, in many practical situations, matrices A and B are structured. Tridiagonal and banded cases are quite common. Unfortunately, the Kolesky QR algorithm for the symmetric definite pencil A minus lambda B described in the previous lecture, when applied to such structured problems, will very often destroy the sparsity even though A and B are banded. The matrix C is equal to L inverse of A times of L transpose minus 1 will in general be full. Thus, this Kolesky factorization algorithm is not practical for large and sparse matrices. The following is the straightforward generalization of the bisection method for the single symmetric matrix A to the symmetric positive definite generalized pair AB. We assume that A and B are both symmetric, tridiagonal, and B is positive definite. The method take advantage of the tridiagonal form of A and B. So the bisection method for triangular matrices A and B. Let's say A is the matrix alpha 1, beta 1, etc. 0, beta 1, etc. 0, beta n minus 1, 0 bn minus 1 alpha n, and B is equal to alpha 1 prime, beta 1 prime, etc. 0, beta 1 prime, etc. beta n minus 1 prime, 0, beta prime n minus 1, alpha 1 n. Define the sequence of polynomials pk lambda given by p naught lambda is 1, p1 lambda is alpha 1 minus lambda times of alpha 1 prime, then pr lambda is alpha r minus lambda times of alpha r prime, pr minus 1 lambda minus beta r minus 1 minus lambda times of beta prime r minus 1 squared, pr minus 2 lambda, r is equal to 2, 3, 4, etc. n. Then it can be shown that these polynomials form a Sturm sequence. The generalized eigenvalues of the pencil A minus lambda B are then given by the zeros of Pn lambda. The zeros can be found by section or any other suitable root finding method for polynomials. Computing a generalized eigenvector. Once a generalized eigenvector or eigenvalue is computed, the corresponding eigenvector can be computed using the inverse iteration by taking full advantage of the tridiagonal forms of A and B. Let y naught be the initial approximation of the eigenvector corresponding to the computed generalized eigenvalue lambda. Then this inverse iteration will be as follows. So for I is equal to 1 to n, so I is equal to 0, 1, 2, etc. Do the following. That is xi plus 1 will be equivalent to a minus lambda b times of xi plus 1 is equal to yi. By taking advantage of the tridiagonal structures of a and b, then form yi plus 1 is equal to b times of xi plus 1. Krylov subspace method for generalized eigenvalue problem. The Arnoldi and Langkos methods described in previous lecture for the standard eigenvalue problem can be applied to the generalized eigenvalue problem. Ax is equal to lambda b. Once the latter is reduced to a standard one, the following are some of the possible cases. If b is non-singular, then GEP is equivalent to the standard eigenvalue problem, that is b inverse of a of x is equal to lambda of b. To apply the Arnoldi or Langkos method to AB B inverse A, one needs to evaluate the matrix vector product, that is R is equal to, we will write it as B inverse A times of Y, which can be accomplished without inverting B as follows. Form U is equal to AY, solve BR is equal to U times for R. One can take advantage of the sparsity of A and B in the computation. Shift and invert A and B are both singular or B is ill-conditioned matrix. In this case, it is advisable to use the shift and invert technique as described below. Let U be the user supplied shift such that A minus sigma B is non-singular. Then Gaussian elimination with partial pivoting can be transformed to the standard eigenvalue problem, that is Cx is equal to mu x, then C is equal to A minus sigma B whole inverse of B and mu is equal to 1 by lambda minus sigma. To apply the Arnoldi's or Langkos method to see the matrix vector products R is equal to Cy can be computed as follows without explicitly computing the inverse. Find the inverse spares matrix, that is A minus sigma B will be equivalent to L of U. Form V is equal to B of U. Solve L of W is equal to V for W. Solve UR is equal to W for R. Symmetric positive definite generalized eigenvalue problem. Here A and B are both symmetric and furthermore B is positive definite. Assume that B is well conditioned, which happens in some applications by like B is equal to L into L transpose with the Kolesky factorization. Then as we have seen before, the Gaussian elimination with partial pivoting, that is Ax is equal to lambda Bx, is transformed into the standard symmetric eigenvalue problem, that is L inverse of A times of L transpose whole inverse x cap is equal to lambda x, where x cap is L transpose of x. The symmetric Langkos algorithm can now be applied to the symmetric matrix. The matrix vector product will be given by like this. R is equal to L inverse of A times of L transpose whole inverse times of Y. Needed in this implementation of the symmetric Langkos algorithm can be computed without explicitly evaluating the matrix, that is L inverse of A times of L transpose whole inverse as follows. So L transpose U is equal to Y for U, form W is equal to AU, solve LR is equal to W for R. Symmetric indefinite generalized eigenvalue problem. Here A and B are both symmetric, but neither A nor B nor a linear combination of them is positive definite. This is the case arising mostly in structural dynamics. If B is non-singular and one wants a few largest eigenvalues in magnitude, one may solve the standard eigenvalue problem, that is B inverse Ax is equal to lambda x, which is symmetric with respect to A or B. If one wants a few eigenvalues closest to a number sigma, the shift invert technique will become like this. A minus sigma B whole inverse Bx is equal to lambda minus sigma whole inverse of x can be used. Choose the shift sigma is equal to 0 if the smallest eigenvalue in magnitudes are desired. Concluding remarks, the shift and invert technique is a powerful tool for the largest and smallest eigenvalues of the pencil A minus lambda B, both in symmetric and general cases, provided a suitable sparse factorization technique of A minus lambda B is available. Otherwise, one can use the generalized versions of Jacobi-Davidson method. So, Krylov subspace method for the quadratic eigenvalue problem. The quadratic eigenvalue problem for large and sparse matrices MDK can be solved by using the methods for the Gaussian elimination with partial pivoting described above once the QAP is transformed into a linear problem. Numerical methods discussed above can be used to solve the linear formulations of QAP, and for example, you see Nastrom, a software package for formulations used for the linear value problems. By using the Bloch-Lanczos method, when implementing a symmetric linearization, the symmetric nature of A and B can be exploited by reducing to a significant amount. Spectral transformation for the QEP problems. An iterative solver such as the one described above is suitable for solving the QEP via linearization to GEP when only a few exterior eigenvalues and eigenvectors are desired. However, if one wants to compute some of the smallest eigenvalues and eigenvectors, then the spectral transformation will be needed first. Computing the smallest eigenvalues and eigenvectors. In this case, a natural transformation is mu is equal to 1 over lambda. This transforms the QEP lambda square m plus lambda d plus k of x is equal to 0 to be inverted to QEP, that is m plus mu times of d plus mu square k is equal x is equal to 0. Assuming lambda not equal to 0, we then have the Gaussian elimination with partial pivoting in terms of lambda. So you will have the matrix. This is the matrix. You do get minus d minus m I 0, b is equal to k 0 0 I, and z is equal to x and lambda x. For the case when m greater than 0 and k greater than 0, we may have Gaussian elimination with partial pivoting matrices like this. That is, A is equal to dm m0, B is minus k0 0 m. Note that A and B are both symmetric but indefinite matrices. Computing the eigenvalues closest to the shift. If one would like to approximate the eigenvalues of the QEP closest to the shift sigma, then we may have used the shift and invariant spectral transformation, which transforms this matrix into this form, where mu will be having like this, that is lambda is the eigenvalue, sigma is the shift. So the exterior eigenvalues mu approximates the eigenvalues of lambda of the original pencil closest to the shift. So you will have this form. Or d cap, k cap, k cap 0, so multiplied with k is equal to this form, you do get this form, if the symmetry is to be preserved. Sensitivity of the linearization, the accuracy of a computed eigenvalue lambda of the quadratic pencil P2 lambda depends upon the type of linearization used. It might happen that for the same eigenvalues lambda, the condition numbers are different for different linearizations, and thus the accuracy will be different. So, as shown that knowing the norm of k and norm of m and norm of d, the structures of the left and right vectors P2 lambda, it is possible to identify which formulas are preferred for the large and small eigenvalues. So, the Jacobi-Davidson method for the quadratic eigenvalue problems. The Jacobi-Davidson method belongs to a family of projection methods applied directly to the QEP. These methods build an orthonormal basis Vk for the subspace Kk and then solve a projected smaller problem. Computing by using the ridge pairs, that is lambda k x cap. So you do get as vectors as V1, V2, Vk. Compute the correction pair V in eta by solving the linear system like this. You do get like this. Obtain the new basis vector Vk by orthonormalizing V against the previous columns of the orthonormal basis matrix. So that is Vk is equal to V1, V2, V of k. Repeat the process until R is sufficiently small. So the above linear system can be written as like this. You do get minus R, which can be solved using the iterative solver such as GMRES. The Jacobi-Davidson method targets one eigenvalue at a time, in contrast with the Krylov subspace method, which can compute several eigenvalues simultaneously. So this leads to local convergence of the matrix. So I am sure that this will give you very nice insight into the how Krylov subspace method can be used for solving the system of equations. I will stop over here. Thank you very much for listening to my lecture today. Thank you once again.